Hi everyone. We have covered different controller types for state feedback, output feedback, and then we also discussed how we can come up with these K matrices, controller gains using pole or eigenvalue placement as well as linear quadratic regulator. And we also did examples in the past several videos. In today's lecture, I would like to step back for a second. I would like to focus on first order systems. And likewise, in the next lecture, I will talk about second order systems. The reason I choose first and second order systems, and because they are very common. Most of the systems we are dealing, especially in the vehicle domain. For example, if you consider aircraft, if you separate if you decouple the dynamics, for example, pitch, yaw, and roll, you can control each dynamics like a second order system. Or if you are controlling velocity of a car, it acts like a first order system. Likewise, the thermal systems act like the first order system. So to make the long story short, first and second order systems are very common. So in today's lecture, I'm going to look at x stat equals to u. Basically, x is a scalar state, u is the control input scalar, subject to some initial condition. And I make a road here. Your actual system may not look like this. It can be some nonlinear system, not necessarily linear, yes, nonlinear system, time varying system. Eventually, you can apply feedback linearization or state transformation based approaches, which um, we do this in my channel in different playlists. If you have difficulty finding it, let me know. But there are feedback linearization or state transformation techniques that can put our much more complicated system into like this one, scalar looking system. And also for most multi-agent systems, we also model agents having this single integrated form. Not bad in practical applications, considering a feedback linearization or state transformation. I mentioned these type of simple systems on the first order domain. For example, when you get responses from your velocity from your vehicle, it acts like this system. RC electric circuits, I already mentioned thermal systems. They look like this scalar integrator or first order system. All right, I will cover two types of controllers for these systems. The first one is a gain K, X minus C. This is how our control law looks like. And I would like to mention this up front. This type of control action is good when you track and when you want to track a constant command C. C is the command that you would like to track. And K here is a positive gain. So directly, since our aim, I want our state X to follow this constant command, so I am forming an error dynamics. I would like to minimize the distance between X and C if we would like to track the command C. So I am looking at error dynamics, taking the time derivative E dot becomes X dot minus C dot. C is constant for now, so 0. So X dot is u, and u is minus k multiplied by e, so minus kx minus c, which is our error. So e that equals to minus ke. This is a, basically, eventually you have e that equals to minus ke. E will converge to 0. But let's pretend you don't want to look at the solution. So let's consider this Lyapunov function candidate. It is positive definite for all errors. It is radially unbounded. When e is 0, it is 0. So it satisfies all the properties a Lyapunov function candidate has to satisfy. So we take the time derivative v that equals to e dot. Now I am inserting e dot, which is minus ke multiplied by e. We have minus ke to the power of 2. Here you can claim asymptotic stability, but we can do more than asymptotic stability since the right-hand side of v dot, if you just do this trick 2, 1 over 2, which is the same thing, I just insert 2 and 1 over 2. So if you look at here, this is exactly like our Lyapunov function. So we can write this Lyapunov derivative like v that equals to minus 2k v And since we have V on the right-hand side, we can claim more than asymptotic stability. We can claim exponential stability for error convergence. So let's do a quick simulation. This is my cleaning routine, cleaning everything. Total simulation time. This is the discretization using first order Euler method. I am choosing gain k to be 1. Why not? So if you increase it from 1, if you choose it 1, system will converge over 4 over 1 around 4 seconds. If you choose it to 4 over 2, 2 seconds. If you choose 10, 4 divided by 10, it will converge around uh, 4 divided by 10, I guess, to 0.25 seconds. So initialization, again, you can copy this code, you can use any initial condition, result won't change. This is the constant command that we would like to track. That's that control structure that you see. And this is a discretized system. The new value of x equals to the previous value plus the computed control action, and the rest for recording, command, state, control, and time, and our plotting routines. You can copy paste, but I'm not going to mention more details about this. This is a simple code. And this is how the system reacts, starting from the initial condition of 0.25. As I mentioned, since gain k is 1, around 4 seconds, it converges and stays there on this command. So this is good for tracking constant commands, and this that rated line is the C. How the C looks like. This is x1. We only have one x in this example since we are looking at the first order case, and this is how the control behaves. Initially large and then gets lower and lower. This was the first case when we have, when we would like to track a constant comment when we have a scalar integrator or first order system. Now, I will shift gears to a second type of controller, which is good for smooth time varying commands. What I mean by that, control also uses C dot. And since you use a C dot, you want to assume C is differentiable. I'm going to discuss when this is not the case or C dot may not be available to you, but let's assume for a second C dot is available and we would like to track time varying commands. So I am using this type of a control structure. Again, I am looking at the error. I would like to minimize the distance between X and C. And E dot is X dot minus C dot. C dot is no longer 0 since the command is not constant. And when you inject x dot, which is x dot equals to u, this dynamics here that you see here, c dot will cancel out with minus c dot. So once again, you have minus ke. It is the same dynamics. So if you look at the previous slide, e dot was equal to minus ke. When our comment was constant, we are not using c dot. Now, this is the generalized case. We have C dot, which is now canceling out here, but eventually we have E dot equals to minus KE. You can use the same Lyapunov function candidate that we used for the case when C is constant. You can arrive, error goes to 0. But right now, error goes to 0, regardless the comment is constant or time varying. So it is a very powerful result. Now, the above structure here you see, I just mentioned, we assume we require actually the knowledge of C dot. And when you generate the comment using some motion planning algorithm, using, for example, splines, radial basis functions, or some functions that are smooth, basically generated as your trajectory, this comment will generate the trajectory that you would like to visit. So you can, to make long story short, what I'm trying to say, if C is generated by such motion planning algorithms, you can easily compute C dot. But if C is not measurable, for example, I am the pilot, my command history C is not pre-recorded, and depending on the situation, I am reacting to a system, so C is not known. So in this case, you can still approximate C dot by using some numerical differentiation techniques or Of course, if you are not, if your measurements are not subject to measurement noise, because if you have significant measurement noise and you would like to calculate the numerical derivatives for C dot, it will be problematic. I will tell you how I do. I usually don't use C or C dot directly if C dot is not available. So when C dot is available, I take C, which is available to me. It can be based on pilot. It doesn't need to be known previously. No one needs to pre-record my response. So C can be real time. C that is not available for different reasons I explained. Let's say you have measurement noise. I take C, pass through this low pass filter. And when you pass through this low pass filter, you can get mu and mu dot. How? For a second, before how, let's say you get mu and mu dot. So you can change this control signal to this one. Instead of using C and C dot, you are using mu and mu dot. So actually here, you are not using the actual command. You are using its low pass filtered version and its derivative of the low pass filtered. And here lambda, if this low pass filter parameter lambda is large enough, then your mu, approximated mu, is very close to the actual command so that you can use this trick if C that is not available to you, but still you would like to track time varying commands, you can just pass through this low pass filter. Now, I'm sure you might be asking how, okay, I can see how you make mu available, but what about mu dot? First of all, I will explain this in code. In code, if you are using first order Euler method for approximating mu dot is the new value of mu minus the previous value divided by some delta, and this variable is generally very small, like 0.005, 0.001 range, representing, for example, if you are using 0.001 for this variable delta, then it corresponds to 1000 hertz of implementation. So it is 1 over the frequency of your microprocessor that you, or processor that you use in here. Usually 200 hertz is not bad, so mu delta becomes 1 over 200, which is 0.005. Anyway, so once you approximate mu dot like this, and look at here, you know, if you insert this to here, then really you are going to get this equation. Basically, the new value of mu equals to the previous one plus delta multiplied by this guy. If you don't see it directly here, take this equation, make this mu plus minus mu over delta equals to minus lambda mu over c. You are going to get these two equations. So in the code, I am using this, you know, since the right-hand side corresponds to mu dot, I am using this for mu dot, and I am directly using whatever this value is, the new value of mu, for my mu variable, then I inserted this control signal. Let's see how it's done in the code. This is the similar code. First, I'm gonna illustrate the case when C dot is available. So K is 1, total simulation is 12 seconds. This is, I am assuming I'm implementing at 200 hertz. So 1 over 200 becomes this delta 0.005. Same initialization, command is sine 0.8t. Since I know it, I can compute this derivative because which is 0.8 multiplied by cos 0.8t. This is the same control signal. I know C and C dot, especially C dot. So I am basically, you know, simulating its response. Since K is 1, around 4 seconds, we can perfectly track this command, which is shown as red dotted line. This blue is X1, perfectly tracks that subject to this control signal. Now, I'm going to look at the case when C dot is not available. I am going to use the same C here, but since it is not available, I am forming this low pass filter. Basically, mu, new value of mu equals to the previous one, multiplied by this delta multiplied by d mu. D mu is the minus lambda mu c. I am initially going to use lambda equals to 2, a small gain for my low pass filter to get mu and d mu dot. Let me show you the results when lambda equals to 2. When lambda equals to 2, this is the actual command C, but the system is slower. It kind of tracks with lag because lambda is 2. It is not large enough. I need to increase it to more precisely track this command. So now when I increase it to 20, if you compare this result with this result, it is not as perfect as this result for the case when you know C and C dot. Still, this is a very good approximation. I can track a time varying comment when C dot is available by applying this low pass filter trick. Again, this is the trick. This is how you can get mu and mu dot from the code. If you have any difficulty understanding any part of the material, let me know in comments, and I will try to answer any questions you might have. All right. Thank you.